Welcome back, this is Professor Xiaoma. In this video, I will demonstrate and explain a specific hands-on problem. Now keep in mind that in demonstrating the hands-on problem, I will use an example dataset, which is default 1. When you do the homework, the dataset is different, so make sure that you adapt the code to work with the homework. In the video, I assume that whatever Python package that we will be using, you have already installed them. If you realize that you haven't installed a specific package and you need to install it in the middle of the video, simply pause the video and go ahead and install it. Install the Python package by following the tutorials that I uploaded. Now let's get started. For this demo, I'm still using the default 1 dataset as is used in many of the other homework videos. To follow this video demonstration, you will need these packages, particularly the NumPy, pandas, and the accuracy score function, the plotting tools, as well as some of the others. And also make sure that you use the exactly same random seed and random state to get the exact same results for comparison. And this demonstration is built on the data that is pre-processed in several other videos, including splitting the X and Y and train test split, building the column transformer to make the one-hot encoding and min-max normalization. So this video will use the processed training and test dataset to demonstrate. Before I begin, let me initialize several variables to prepare for modeling. These are quite similar to the Adeline model. And again, I'm using an eta of 0.01. This time for logistic regression, it's more reasonable. Let's run this. I got these initial values for the parameters. So the implementation of logistic regression is actually very similar to that of the Adeline model. Let's take a look at the process codes inside the loop. Here is the process list for implementing inside the loop of the logistic regression. The only differences are that the activation function is different. You will use sigmoid function instead of linear, which is equivalent to doing nothing. The sigmoid function is different from the linear activation. And the very last step of the for loop, constructing the complete for loop, when you calculate the cost value, the cost function is somewhat different from that of the Adeline model. These are the adapted codes for logistic regression, and let's take a look. The decision process is exactly the same. In getting the net input function z, you would use the same formula, and this time, compared to the Adeline implementation, only the X data set is slightly different because now we have split it into train and test set, and the train set has been processed by the transformer, so it's the X train processed. So let's run that. Now I'm printing the first 9 elements of the Z and make sure that you get the same values. So the difference of logistic regression begins with the activation function. The activation function is the sigmoid function. Because you are familiar with the sigmoid function, you can see that this line of code computes the sigmoid function, putting the z net input inside the exponential, and there's a negative sign before the z net input. And before applying the sigmoid function, another line of code makes sure that z value does not become huge or very small, because even that when that happens, the sigmoid function value will not be very different because of the S-shaped curve. To limit the amount of computation that's required, every time the extreme value happened, we just want to clip both ends of the extreme values to save computation power without affecting the final result. And after this, I'll print the first 9 elements, make sure that you get the same results as I show here. Now the rest steps are exactly the same inside the loop before calculating the costs. These are the same as the Adeline model implementation. Calculating gradient descent. Make sure you get the same values. Calculate weight update. And getting all the delta weight. Then update the weight. The old weight and the new weight. Similar to completing the Adeline model implementation, we need to put the for loop together inside the loop and run the loops in order to train the model. But again, before I do that, I reinitializes all the values because I want to start from fresh and make sure that I get the same values. So run this, get the same initial parameter values. Now putting the loops together, I simply copy and pasted all the codes inside and comment them appropriately. But before the for loop, you want to make sure that you create an empty list to store the cost function values. And within each loop, you want to also calculate and save the cost. So here is another difference between the Adeline model and the logistic regression implementation. The cost value computation is different. Now for more details, refer to the timeline with notation map cheat sheet to find how this cost function is derived and why this Python code makes sense. Now as shown on the screen, the cost function is here. Now let's run this. Let's review the values of the cost function. I will print the cost function's values, keeping only 3 decimals. Now observe the pattern of the values. The cost values initially increased but then quickly reduced, and it follows a declining pattern, which means the learning process is on track. The ADA learning rate is appropriate. Next, I will plot a line chart to look at the trajectory. The code for making the plot is almost very similar, almost the same as one in the Adeline model implementation. Now as you can see, the trajectory is good, the curve is flattening, although it's still learning. So maybe I need 10 more epochs. So next I will restart the process, I will reinitialize, and I will retrain the model with more epochs, but keeping the learning rate and everything else as the same. Okay, so here is the code. I will reinitialize with the same initial values, only change the epochs, but I combine the initialization codes and the for loop optimization codes inside the same cell. The model is trained. Next, I will print the values of the cost, similarly following the decreasing trajectory, and make a plot of the values. Only change the x ticks. The trajectory continues, it's still flattening, although it seems to be still learning. But the model should be trained adequately. Let's evaluate the performance. Now this time using both train and test set to see if there is any difference between them. I will first assess the test set. These codes are very similar to the one in Adeline implementation. The only difference here is that the activation is different, and also added the clip function to save computational power. But then I use the same threshold of 0.5 because the target variable has not changed. Now let's run this. This model achieved an accuracy of 0.937, pretty good. Although not as good as the Adeline model after 20 trains, and this is mostly because of the nonlinear activation function that made the learning a little bit slower. Now let's evaluate the test set. Running the same code, only changing the X train to be X test, and when evaluating accuracy, change the Y train as a ground truth to be the Y test. So this model actually did not have any information about the test set. The test set is almost unseen data to the model. And let's see how it performs. The model achieved a very similar accuracy level of 0.92. And because performance level is pretty high, and there is not a big discrepancy between the training and test set accuracy, the conclusion for now is that there is not much overtraining on the training data. The model is not overtrained because it has only been trained for 20 epochs. Now, for just a few training, the model typically picks up the trend very well and tends not to be overfit. But does this really mean that the logistic regression cannot overfit? And we will have to train for a longer time to find out. So let's do a quick experiment to find out whether this logistic regression will be overfit to the model. What I will do is to train for a long time, to train a large number of epochs while keeping everything else as the same. And still I will start from the fresh. So let's do this. I didn't change anything except for the number of epochs. This time I'm training for 10,000 times. If anything, if the model is prone to be overfitting, it will definitely be overfitting after 10,000 epochs. Let's run this. And let's plot the cost values. Now it's quite clear the learning curve has already flattened. It's very flat. And it reached almost flat level by 1,000 training epochs. Let's evaluate the performance on the train and test set. Run this. Wow. The accuracy on the train set is 100% accurate. There is zero incorrect classification. What about the test set? The model also made fewer mistakes on the test set and achieved an accuracy score of 0.988, the largest ever since. The model is not overfit to the training data, even with such a large number of epochs and a long training time. How can this be? So the truth is that this dataset is a simple case. Now this dataset is a subset of the original dataset, but in this subset, the target values of the two class labels are linearly separable, which means that with a well-trained and designed model, the model can separate the ground truth in the dataset very well. Even with a long time of training, this model is actually overtrained. I will show you the evidence. But even with that, the performance on the test set is still pretty good. And this is precisely because the dataset is a simple case. It will be very hard for the model to mess up on the test set. You can read the details here. To show you the signs of overfitting, let me print out final weights after a long time of training. And I have sorted the largest and smallest weights of this long list of weights. Most of them are good in the range of between 0 and 1, but the largest coefficient is 49.52. With normalized x variables, the coefficient of this magnitude is uncanny. This means that model has been overtrained and the model is trying to fit the training data very well, and that's how it can make zero mistakes in the training set by having extreme coefficients. However, this model will definitely perform worse in unseen data, but still, because the train and test set come from the same subset, model cannot mess it up even with a long time of training. This demonstration is completed. I hope you enjoyed it.